Do you sometimes feel tired during meetings? Or do you sometimes have a headache after work? Do you want to change that? Then this video can be interesting for you because we will measure harmful gases in your environment, which can trigger both. Grüezi YouTubers, here is the guy with a Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. In this video, we will focus on indoor climate and we will concentrate on gases where the primary cause is humans, not machines or lousy building materials. We will look at CO2 and its influence on indoor air quality and your well-being and how it can be measured. We will see the relationship between our CO2 sensors and global warming. We will use a second way to assess indoor air quality, VOC or eCO2. And we will build sensors which transfers the measured values via MQTT into Grafana. Let's start. We all know what fresh air is, and we all remember the difference when entering a meeting room packed with people. But how can we measure this difference? The easiest way is to concentrate on gases which are produced by humans. The first gas that comes into our mind is carbon dioxide, or CO2. These days, this is a famous gas in global warming discussions, and we will later learn why. Its significance for indoors climate comes from the following fact. Humans need oxygen to live and produce CO2. By breathing, we change the percentage of the different parts of the air around us. But what are the components of fresh air? According to NASA, outside air consists of 78% nitrogen, 21% oxygen, and 1% others, including CO2. So CO2 does not seem to be a problem because it is quite rare. Besides that, CO2 has no odor and also no color. So why to bother? Low oxygen levels are dangerous for humans, as we see here. We could measure oxygen levels to assess this danger. For example, in our car, a so-called lambda probe measures oxygen in the exhaust gases to check if the engine burned fuel correctly. But these sensors are not used for indoor applications. Maybe they are too complicated, too big, or need too much energy? I do not know. Fortunately, we can go the route of so-called secondary indicators. Because we inhale oxygen and exhale CO2, we can use this gas as an indicator of the oxygen level, at least in our offices or living rooms. The more CO2, the more people consuming oxygen and the lower its level. As soon as we let fresh air in, more oxygen and less CO2 will be present. The CO2 level, therefore, is a perfect indicator of the indoor climate. Simple. Unfortunately, CO2 sensors are quite expensive and also have a slow reaction time. That's why a secondary indicator is used for the same purpose: transpiration of humans. Humans do not only exhale CO2 while sweating, we also create H2, ethanol, and other gases in small quantities. They are part of volatile organic compounds, short VOCs. From a chemical perspective, they are entirely different from CO2. But because one of their sources, human bodies, is the same, we can use them also as a secondary indicator. Sensors that measure these gases are cheaper and react much faster than CO2 sensors. But because humans are not the only source of VOC, they respond differently, as we will later see. So we can say humans are the primary user of oxygen and the primary source of CO2 and VOCs in typical office or living rooms. If we monitor CO2 or VOC, we either can warn people to open the window before they lose performance or before they get a headache, or we can switch on the automatic ventilation. The next question arises: How do we measure CO2 or VOCs? As said before, CO2 is odorless and also has no color. This is not entirely true if we look at the whole spectrum. CO2 heavily absorbs waves with a wavelength of 4.26 micrometers. For a comparison, green color has a wavelength of 0.5 and infrared light for remote controls uses a wavelength of 0.9 micrometers. So we need sensors that detect light in the 4 micrometer range. We know this range from our FLIR thermal imaging cameras. They work from 3 to 12 micrometers. And here we see the relevance of CO2 for our climate. The visible sunlight passes the atmosphere without substantial dampening and reaches the ground. Here it warms the soil and is converted into heat. As we saw, CO2 blocks this radiation from escaping back to space. So the heat stays with us, which is okay for me in November in Switzerland, when temperatures are low. A little warmer would be welcome. Coming back to our topic, all current CO2 sensors work like that. They consist of a particular IR diode, a distance where the air can enter, and an IR detector, usually with a filter for 4.26 micrometers in front of the sensor. That's all. But because the CO2 levels are minimal, these parts must be produced in high precision. Here I have two such sensors. The left from the Swiss sensors specialist Sensirion and the right one from the Chinese manufacturer Winsen. Both are not cheap. Interestingly, the Sensirion sensor is less expensive at DigiKey than on AliExpress. The SGP30 works on I2C and the MH-Z19 on serial. Both work with 3.3 volts and are 5 volt tolerant. And for both we find libraries. I have a third one from a German sensors company, Sensirion. Unfortunately, I was not able to get it running, also because no Arduino library exists. But before we start to use them, we have to understand their limitations. The Sensirion provides an accuracy of ±30 ppm, plus 3%, and the Winsen ±50 ppm, plus 3%, which is, as we will see, good enough for our application. Sensirion guarantees a lifetime of 15 years, and Winsen says more than 5 years. Why is this important? Because these sensors typically are forgotten sensors in equipment like ventilation and nobody cares about them. But the ventilation easily can malfunction if the measured values start to be wrong. And here we enter an essential area. CO2 sensors have to be calibrated from time to time. Fortunately, we can use a trick. The outside air at sea level currently contains around 400 ppm of CO2. I say currently because, as we see here, it is changing over the millennia. So we might have to calibrate our sensors to a higher value in the future. More important, this value is reduced by about 3% for every 1000 feet or 300 meters altitude. If we want better measurements, we have to do this compensation already now. And we see a trick to avoid global warming. Just move to a place above 3000 meters. Then your CO2 levels are at 300 ppm. Problem solved. Joking aside, you can easily calibrate your sensor by putting it outside your home and note down the value to calibrate it. But most of the sensors are fixed inside buildings. To calibrate those sensors, you can assume that the lowest measured level is around 400 ppm and adjust the readings accordingly. Both sensors do this automatically if you select the function. But it can take a few days till this calibration is done and the sensors display accurate numbers. The SGP30 also have a feature to compensate for pressure. You either have a pressure sensor available and use its values, or you enter an average value, or also the elevation of your location to get closer to reality. For the MH-Z19, you have to do it in your sketch. It always calibrates to 400 ppm. Another fact you have to pay attention. After startup, the values are imprecise. Only after 30 minutes or so they are okay. This is not a big problem for indoor air monitoring, but it can be a problem if you want to do measurements for experiments where values change quickly. CO2 sensors are no low-power devices. According to the datasheet, the SGP30 consumes 19 mA and the MH-Z19 consumes more than 60 mA with peaks up to 150 mA. And both should not be switched off. So battery-operated devices would need a massive battery. Coming now to the VOC sensors. Also here I have two sensors. The SGP30 from Sensirion and the MICS6814 from SGX SensorTech. The SGP30 from Sensirion measures two gases, H2 and ethanol. The MICS6814 has three sensors and claims to detect many more gases. But it has analog outputs and its interfacing is quite complicated. This is why I did not use it for my tests. Both sensors use a so-called hot plate with a metal oxide surface to detect these gases. Fortunately, the SGP30 is tiny, so the heating of the hot plate only takes 48 mA. The MICS6814 consumes around 100 mA. These are also not sensors for battery-operated devices. The SGP30 runs on only 1.8 volts, but the breakout board has a voltage regulator and level shifters and works with 3.3 and 5 volts. But what can we do with these two raw measurements? The SGP30 uses these raw measurements and outputs two values. One is called TVOC or total VOC and the other ECO2 or CO2 equivalent, which is an artificial number that should somehow match the CO2 values. We will later see if this is true or not. In the next step, I built three sensors, two with ESP8266 and one with an ESP32. Why? Because I wanted to connect them to my Grafana dashboard, of course. So all sensors send MQTT messages to Node-RED, which feeds it into InfluxDB. In the end, Grafana integrates the values into other weather and indoors data and shows nicely looking graphs. You find videos on this channel explaining how to create such diagrams with your Raspberry Pi. Here are the measurements for the last 2 days. All sensors were in my lab at nearly the same place, about 50 centimeters away from me. Yesterday I came to the lab before 8 AM and the SGP30 had an issue the night before. During the day I was a lot in my lab, but not always. And after 16 o'clock I had a Skype call and had to close the door of my lab to not disturb my wife. The first observation is that all three values correspond somehow. The blue one is the ECO2. Around 18 o'clock and also this morning it shows higher values than the real CO2 sensors. Please do not think that I'm a nerd and therefore personal hygiene is the reason for that difference. Dishka, for example, could contribute more in this respect. If you do not believe me, try to wash your cat and do not complain about the scratches. The MH-Z19 seems to react a bit faster. But maybe I did not use exactly the same sampling strategy for both sensors. And be aware, we are at the beginning of the measurements and the calibration process is not finished yet. I will leave the sensors on and see how they behave in the future. But looking at this table, it becomes clear that we do not need a high precision to qualify indoor air quality. This might be different for other applications. Looking at the curves, we see how fast the values can go above 1000 ppm when I close the door. This is not yet a problem, but I was nearly alone in the room. Only Dishka helped me with CO2 production. but because of her typical low activity behavior, she does not contribute a lot. This changes if you, for example, have a class of 20 people in school or 15 people in a small meeting room. Then these values can increase fast. I think each classroom with closed windows should have such a sensor. Because school is hard enough and bad air quality should not be the reason for sleepiness. I think other causes like late gaming or using apps on the smartphone, and for the elder, drinking too much alcohol during nights contributes enough to sleepiness of children in school. Maybe one of you guys creates a cool project which then could be used to build such a meter by the students. I would create the video for the assembly. Promised. But coming back to the sensors. First we go outside and we see if they really show around 400 ppm. That seems to be okay. The VOC sensor also measures 400 ppm, but I suspect that the algorithm adjusts values below 400 ppm. But how can we create CO2? The simplest way is to use our body and exhale the air into a small container. Fortunately, CO2 has a bigger mass than air and therefore stays at the bottom of the jar, even if we do not close it. By the way, fire extinguishers use this effect. If you want to protect a data center against fire, a sprinkler would probably not be a good idea because water quickly causes a lot of damage in such areas. Therefore, they use CO2 to fill up the whole room. As seen before, it creeps below the oxygen and displaces it. Without oxygen, the fire stops. Problem solved without collateral damage. As you see, my exhaled air contains a lot of CO2, and it takes a few seconds until the CO2 sensors read these high values. The VOC sensor reacts much faster. This can be useful for specific applications where speed is essential. Next, we do the solder test with all sensors. The CO2 sensors are not very much impressed. The VOC sensor shows very high numbers for eCO2 and TVOC. And if we put a banana close to the VOC sensor, it also indicates higher eCO2 values. But the air around the banana and the solder fumes do not contain more CO2. This effect is also visible in the diagram where we see the measurements of a proper CO2 and a VOC sensor placed in a room of a schule building. During pizza cooking, the VOC measurements were very high. I'm pretty sure pizza odor does not trigger complaints about drowsiness or sleepiness, at least not with young people. Summarized, we learned why CO2 could be used to assess indoor air quality. We saw the difference between a primary and a secondary indicator and when they can be used instead of primary indicators. We saw how CO2 is measured and that the same effect can isolate the Earth and increase its surface temperature. We used a different secondary indicator to assess indoor air quality, VOC or the calculated eCO2. It measures gases in human transpiration. We built sensor nodes to transfer the measured values into Grafana. Comparisons of the three sensors showed that the measured values were different. The two CO2 sensors were quite close and the VOC sensor in some situations was off by 30% and more. Playing with the sensor showed that it is easy to produce and store CO2. Exhale in a container and, because CO2 is heavier than air, it stays there for a while. We saw that soldering or placing a banana in the proximity of a VOC sensor made its values increase. CO2 sensors stayed roughly the same. CO2 sensors are more expensive than VOC sensors, so you decide which one is good for your application. I will stick with both because of the soldering. The Sensirion CO2 sensor is much more expensive than the sensor from Winsen. For a maker project, the cheaper is definitely good enough. For industrial applications, a trusted supplier for sure is the better choice. By the way, Sensirion just presented a new CO2 sensor based on acoustics, no more on IR light. It should even be smaller than the current sensor, and microphones probably are also less sensitive to dirtying than optics. Maybe I will get one from them for a test. One last thing. Air conditioning and heating of vehicles consume a lot of energy. For conventional cars, this is not a huge problem because they produce a lot of extra heat. If you use electricity, however, this is no more the case. Air conditioning can eat up to 30% of the overall energy consumption. Therefore, knowing when to exchange the air inside the car can lead to smaller batteries or bigger range. I hope this video was useful or at least interesting for you. If true, please consider supporting the channel to secure its future existence. You find the links in the description. Thank you. Bye.